My name is Jon Sensinger, and I am speaking to you today from the unsurrendered and unceded traditional Wolastoqey land. The lands of Wabanaki people were recognized in a series of peace and friendship treaties to establish an ongoing relationship of peace, friendship, and mutual respect between equal nations. The river that runs by our university is the Wolastoq, along which live Wolastoqeyik, the people of the beautiful and bountiful river. But the story I'm going to tell you today took place mostly at the Rehabilitation Institute of Chicago, located on the traditional unceded homelands of the Council of the Three Fires, the Ojibwe, Ottawa, and Potawatomi nations. Since then, I've become the director of the Institute of Biomedical Engineering at the University of New Brunswick, and RAC has changed their location and name to become the Shirley Ryan Ability Lab. So I want to talk to you today about prostheses design, and specifically small prostheses. The majority of prostheses are designed for someone who's a 50th percentile male, meaning if you lined up 100 males, average males, your smallest would be first percentile and your largest would be 99th percentile or 100th percentile. Most prostheses are designed for 50th percentile males, but that means they're too large for 50% of males and the majority of females. And so we said, what if we designed a prosthesis for a 25th percentile female? Then we could easily scale it up for larger people as long as it had a relatively sufficient speed and strength. And so that's the goal that we set out for. And we were pretty successful. We were able to get a prosthesis that was just as fast and just as strong as commercially available prostheses in a self-contained package, and yet was as small and as light as a 25th percentile female. And of course, the way we were able to do this was through developing motor and transmission technologies, and that's the story that I want to talk to you about today. Really, I think there were three lessons that we learned throughout this process. The first was that all prosthesis motion is dynamic acceleration bursts. It's not a constant speed. You're stopped, you make a movement, you're stopped again. That means there's dynamics involved. And so we found that conventional motor metrics were really not indicative of the performance of the motor designs that we needed, and I'll tell you a bit about that today. We also found from our DARPA work that energy equals weight. So you can't just ignore the efficiency if the battery has to live within the weight confines of the prosthesis, and therefore efficiency of the mechanism is very important. And finally, we found that customization is really helpful. And so we found ourselves going towards technologies that were developed by other industries, but that were able to be customized so that we could tweak them for our specific applications. And I'll tell you about a couple of the technologies in particular that we customized for our prosthesis. Okay, so the first thing I want to talk to you about is motor metrics. So when you're trying to size a motor for your particular application, you can look at a motor manufacturer spec sheet and they give you a variety of parameters. And which one do you use when you're choosing a motor? Oh, that's a good motor. Oh, that motor's not so good. And specifically, if you're designing for robotics, how do you choose a motor? One of the interesting things about robotics, which is a relatively niche field compared with all of the other motors that are used in the world, is that they typically have a limited range of motion, and they typically have high bursts of speed. And if you have a high burst of speed, that means you're going to have high acceleration. And high acceleration, given the inertia of the device, means that you're going to have high torques at high speeds. And the combination of high torque and high speed is that one spot you don't want to be in a motor design. And so it becomes the weakest link in the chain, so to speak, or the Achilles heel. We can look at this by looking at the torque versus speed of a given motor. So a given motor can produce a maximum speed and a maximum torque. And relatively speaking, there's a linear trade-off between the two, which is limited by the resistance of the motor. How much current you can push through the windings limits the available voltage, and the voltage in turn determines the speed at which the motor can go at. So there's a linear relationship between the two, and we can accordingly think of a motor as having an envelope of speed-torque combinations that it can do. We can then plot a profile of a given task with given dynamics, given inertia, given kinematics. And so, for example, we can say, what if you're carrying a very heavy object, but you're moving relatively slowly from one position to another position? Well, in that case, your torque speed profile will look something like this blue curve. And you can see we're relatively close to the envelope of the motor, but we're okay. We could say, well, what if I'm carrying less weight, but I'm moving a bit faster? Well, we can see that's not going to be any issue for this particular motor. And finally, we could say, well, what if I'm moving really fast? Well, you can see here that we're completely fine in terms of speed. We're well below our maximum speed. But ironically, we're coming pretty close to that diagonal line of speed and torque. And so it's the high speed task that may limit us. And it's not just because of the speed, it's because of the torque that's required due to the inertia and the acceleration. And so let's take a closer look at this plot, and let's talk about it in terms of some of the metrics that are available in commercial tech sheets. So many of you will be familiar with the stall torque or the torque constant of the motor, and of course those map to the maximum torque that the motor can produce, or the torque that a motor can produce for a given amount of current. As well, we can normalize that by the inertia of the motor and talk about the power rating. We can also look at the area, and interestingly, the area of this envelope is equal to the maximum power. And this is a rating that's commonly used by non-roboticist motor designers. They want to know what's the power rating of this motor. It corresponds to the area, but we don't necessarily care about the area. It really depends on the profiles of the tasks that we envision for these robots. Now, a similar idea to the area is what's called the normalized power, and this is just 1 divided by the square root of the resistance. So there's a motor constant. A motor constant is independent of the windings of the motor. Motors can be wound with different windings. And we see that the motor constant kind of blends together the stall current with the normalized power concept. There's the maximum acceleration, and it turns out that this is equal to the motor constant normalized by the inertia of the motor. And then finally, the one that we have found to be most useful is called the speed ratio. And this is equal to something similar to the maximum acceleration, but the motor constant is squared. I'll talk to you a little bit more about that. So what we found is that if you set your motor envelope given a particular motor, and if you set your task given the profile that you wish to achieve, you can mathematically rearrange the motor parameters from the task parameters. And we did this in a paper that we published in IROS, so you can check out the paper for the derivation of that. So essentially you're saying, okay, I can get this speed constant from the tech sheet, and then I can calculate the value using this equation, which is available in our paper, as a function of what's the torque, what's the speed, what's the acceleration, what's the voltage, and what's the current. Now, most tech sheets actually don't report the speed ratio, but they do report the speed constant, 1 over tau m. And so this information is readily available on almost every tech sheet, and so you can use it to predict whether a given motor is a good motor or a bad motor for your specific design, regardless of the task that you have. And so we have a couple of assumptions here. One is that you can wind a given motor for your task. And so when we're designing motors, we're looking at the general architecture rather than the specific winding. We're assuming that we can wind it. There are several companies that will do custom windings for you. 2 that we've used are Emotech and Go Brushless. And also we assume that you can choose a range of gear ratios. And I'll talk to you about that in just a minute. We've used harmonic drives and cycloid drives in the past. Some gear transmissions cannot achieve a large range of gear ratios while maintaining a constant efficiency. Planetary gears are a good example of that. Okay, So I just want to leave you on this point with a simulation study that we did where we did a range of tasks. We looked at the motor envelopes and we said, did the particular motor, was it able to achieve the tasks that we wanted? And then we compared a variety of metrics. And you can see that the rated power doesn't do that well. It can only predict about 60% of the success rate for real-world applications where we're having motors do dynamic tasks, ballistic tasks. And you can see that the speed ratio, while still not perfect, does a much better job of predicting whether a given motor is going to be suitable for a particular set of tasks. Really, at the end of the day, you have to look at the motor envelope in order to see if a given motor design is going to work for you. But as a quick approximation, just sorting through all of the motors available, speed ratio does seem like the metric that's the best for getting a quick guess on the power. Okay, let's transition to talking about, now that you know a general architecture for your motor, how can you tune, what should you be looking for in designing the motor? So at least for prosthesis design, and I think for most robotics design, stronger is better. So if we have a given output torque, a higher motor torque means that we can use a smaller gear ratio. And smaller gear ratios are really beneficial for most applications in robotics. If you have a smaller gear ratio, that means that your gear is spinning slower. And that means that it's quieter. So if you care about sound, you want a high torque motor. Also, typically, a smaller gear ratio will be more efficient. So as long as you can maintain your efficiency of your motor design, you'll get an added benefit of efficiency in your motor. Typically, smaller gear ratios can be smaller, and they also take less weight. And at least for prosthesis design, transmissions are about 2 to 3 times of the motor mass. So they're a significant part of this weight equation that we're always trying to minimize. We found that exterior rotor motors are really good for delivering high torque applications. Interior rotor motors are much more well known in robotic applications. Maxon, Faulhaber, and Emotech have all conventionally done it, although Maxon's recently switched over to exterior rotor motors as well. Exterior rotor motors, ironically, are better known for CD-ROM drives and hard drives because they can spin at incredibly high speeds without the magnets ripping off due to centrifugal force. But recently they've been used for RC airplane and drone design, and they can develop pretty high torques in those applications. So we've done a variety of studies. We've done simulation studies, we've done experimental studies, and we've consistently found that exterior rotor motors have more stall torque, better efficiency, and they use less power than similarly sized interior rotor motors. We've done a variety of empirical studies. This is an example of a motor that we had custom wound for us. It's about the size of a United States quarter. And you can see whether you're looking at speed ratio density, which we think is the best, or motor constant density, or even stall torque density, the exterior rotor motors are consistently substantially better per weight than interior rotor motors, regardless of the company that's making them. There are some concerns when I go to conferences, and when we have the discussion today, some of you may want to talk to me about some of these concerns. There are some common concerns that I get asked about switching over to exterior rotor motors. How do you do heat sinking, for example? We found that we can heat sink from the back. Some people are concerned that the rotor itself is only supported on one side, but the existing hobbyist designs have really solved this problem. They've got a double bearing design, and that does a good job. You do have more inertia because the spinning part has a larger diameter. It's the exterior part. But we can get away with a plastic rotor shell using some tricks of the trade to keep the magnet flux working with very thin flux rings. And so we're really able to reduce the inertia of the rotor. Some people say, well, historically they're used for high speeds, but that's only because of centrifugal force. And a lot of people say, well, they're not commercially available, but they're becoming more common. Maxon is now producing motors that are exterior motor rotors. And many hobbyist companies are willing to wind drone motors for you, although they'll often caution you that they don't think they're going to fly, which is fine. We're not using them to fly. Two companies in particular are Go Brushless and Castle Creations. There's many more that are available as well. Okay. So finally, let's transition to transmission design. So as I mentioned earlier, at least for prostheses, transmissions typically weigh at least twice as much as the motor. And transmissions are typically inefficient at the high ratios that we need, which then means we need heavier batteries. So transmission design is really, really important for prostheses, and in my experience, for a wide variety of robots. As I mentioned as well, we've done systematic noise studies in anechoic chambers, and most of the noise that we hear from a robot is coming from the transmission itself. And then transmissions see the highest stress, the highest impacts in most loads, unless you're using a series elastic actuator type application. And so durability is a strong concern for transmissions. In the past, we've used harmonic drives. Harmonic drives are an excellent transmission. You can get very large transmission ratios. They typically have about 70% efficiency regardless of the ratio. So for small ratios, that's not that impressive, but for large ratios, that's actually quite an impressive efficiency. They're very strong, they're very compact, and they're accordingly used by a variety of robotic companies, including RoboDrive, Waseda, MIA, and Liberating Tech Prostheses. But today I want to talk to you about cycloidal drives, and cycloidal drives are very similar to harmonic drives in topology. Harmonic drives have an elliptical input, and cycloid drives have something that's essentially similar, only it's an offset cam. They both have 3 parts instead of 2 parts in terms of topology. There are some differences between the two. The high inertia part for a harmonic drive is the input. So that means the high inertia part is spinning at high speeds. For cycloidal drives, the high inertia part is the output, meaning it's spinning at low speeds. So in terms of reflected inertia, you're better off with a cycloid drive. But in terms of backlash, harmonic drives don't have any backlash, and that makes them very popular for a variety of robotic applications. Cycloid drives have common backlash, can be designed around, but it's similar to a planetary drive where you're always going to have a little bit of backlash. Here's a couple of videos of cycloid drives. The eccentric disc is driving a custom designed cycloidal drive, and you can play around with the profile of that to get pretty high efficiency. It's a very large gear ratio in a small package, and cycloids roll instead of sliding, which makes them efficient, quiet, and very strong and very durable. There are some limitations to cycloid drives. The resolution, if you're going for very small sizes, is typically limited by the technology that you use to manufacture it. We've used wire EDM to manufacture it. There are some concerns with the finishing of wire EDM, but we haven't had any issues with that. We found that as long as you wear them in over a course of a couple hours, that the efficiency is really good. The bearing force ends up being one of the key limitations for cycloid drives. There's a very large force on the bearings, and it's related to the gear ratio, the amount of eccentricity, as well as the output torque. And so we've spent a lot of time looking for needle bearings and other bearings that can withstand those high forces. That's probably the key limitation of cycloid drives. As I mentioned, backlash is an issue with cycloid drives, but for applications like exoskeleton design and prosthesis design, it's relatively small. And we found that actually fixed roller designs are better than free spinning roller designs. And this is particularly helpful for small applications like a lot of roboticists need. And there's a good paper that talks about you need a very specific curvature if you're using a fixed roller design. And we're using the one from the paper referenced here. Works very well for us. So in summary, we've had a lot of luck creating small prostheses. The video I'm showing here, ironically, is on a very large male subject but the prosthesis itself is a 25th percentile female prosthesis. It works very well. We've had to look over and over and over to find the weakest link and then tackle that weakest link. And we've really tried hard to leverage existing technologies, not to invent new technologies, but to make sure that those technologies were customizable so that we could really dial them in, go through all the simulation exercises, and find those rooms for improvement, and then improve them through frequent rounds of iteration. So I look forward to talking with you in the open panel discussion. This project, as I mentioned, was done at the Rehabilitation Institute of Chicago about 10 to 6 years ago, so a lot of development has happened since then. There's a fantastic lineup of speakers at today's workshop, and I'm really looking forward to learning from them and seeing what the newest developments are, and talking with them and you about possible explorations in the future. Thank you for listening, and I'm looking forward to seeing you in the open panel discussion.